So I wanted to shoot a video on the pumpkin project I'm building this year. I know that we are not going to be able to do the same kind of like Halloween, like trick or treating or anything like that this year because of the pandemic. But I still like the tradition. I like the like being creative and trying to figure out something cool and new to do each year. So I was thinking about what I was going to do this year, and I have this treasure chest that I recently designed a linkage for to open and close with the servo. So I figured what I would do would be to hook up an ultrasonic sensor in that servo, and then an LED strip, and basically when you walk up to the lid, have it like open and close. Maybe I'll add some other stuff, but the gist is open and close the lid, play a light animation based on the distance someone is away from it. So I went through and actually fit in a whole bunch of the code for it earlier, and then noticed I didn't have my microphone on, which I'm like looking at right now. I can see that it's on. So I figured I'd go back and just do it again. That's how much I hate video editing. So the main parts of this that I want to fit in are the servo, the ultrasonic sensor, the LED strip. After that code is fit in, there's like all this other stuff that I need to do as far as like introducing a state machine and then tying the output of the ultrasonic sensor together with the signal to the servo. But at the very beginning, I just want to fit all the stuff in. So I've got a blank sketch here. I'm writing this one in C++. Arduino's version of C++, and this is like the bare minimum you need for a sketch: a setup and a loop. The setup will run once; it's like a constructor almost, and then the loop will run multiple times per second based on how fast your microcontroller is running. So the first thing that I will do is go through and set up the servo. It's fairly simple. So let's do this. Say include the servo library. And then we'll need to instantiate an instance of the servo. We'll call this the lid. So, and now that we have that, well, actually we also wanted to define the pin that the servo is connected on. So I already hooked up the circuit, so the servo pin is on pin 0. Actually, I'll call this lid pin. Just keep the naming consistent. So let's see. Let's do. Open the serial output so that we can see, like, we can output some text and figure out what we're doing. Starting up, we likely won't see this unless we put in like an arbitrary weight. Let's see. Get the top loop message going, just so like this way we can like kind of like see outside of the hardware. We can see that our loop is running as expected, that we're getting to the places that we're running and stuff like that. And then let's see. So the lid, we need to attach the pin. Okay. Got we've attached the lid pin to the GPIO pin that we want to tie it to, and then also we want to start at we're gonna do this. Let's do a sweep to make sure it works. So we'll sweep between 0 and 90. I'll explain what we're doing. And then we'll say lid right 100 milliseconds, and then so that'll sweep us open, and then sweep us close. Okay, so basically what we're going to do is the servo takes, you control the servo via pulse width modulation. So So it's basically like a fake sine wave that we're sending from the code. And the servo library facilitates that. And we can use that to like, instead of sending out the pulse wave, the pulse width, we can tell it the angle that we want the servo to move to. So I know from the previous video that I recorded on this that that we want the angle for this particular lid to be between roughly 0 and 90 degrees. This servo can go all the way to 180, but if we do that, we overextend the lid. So yeah, so talking. Let's actually hold on. Let's print out the I value so that we can start visually tying the angle number to the movement. And actually, I've got my oscilloscope hooked up so we can also see the square wave that's being generated by the pulse width modulation. So once this upload is done, where did our error occur? Doesn't seem to be the code. Let's see. Let's restart everything just to be safe. So, and I've got power coming in from my from the benchtop power supply. Let's see, so it's sending in a 5-volt signal. Here we go. Then the logic's coming, the power's coming from the microcontroller. Why are you acting so funny? It should open quite a bit more. It's almost like the starting position. It's almost like the starting position is wrong. So let's just hard code. Let's hard code the starting position before we even attach the servo and start sending signals. What's going on? Huh. So, I didn't think I'd have to be doing this kind of troubleshooting, but it's worth diving into. So, I'm going to compare it to the previous code I had written. Increment, decrement. Oh, what am I doing? So, we're going up. We're not coming down. Actually, hold on. Before I upload this, let's open the serial monitor and see the values. So we're hopping up to... Yeah. Okay. Wait a minute, what? So we go up to... Huh. Oh! Wait a minute. Whatever. So we're going from 0 to 90, which we expect. And then are we kicking out of this? So we start with I being set to 90, and if I is greater than or equal to... Whoa, wait a minute. Let's change it back to what it was. Coding. So I is set to 90, and we're saying if I is less than or equal to 0, decrement, or not less than or equal to, less than 0. Kick it down. I mean, like, why would this be... It's weird. I feel like we should be seeing a different output here. We're hopping all the way up to 90 for that first loop. And then we're starting over by saying I is 90. And then we're saying 90, if 90 is less than 0, which is false. Oh, duh. I'm an idiot. Okay, because we're kicking out early because that is false. So this, because the loops in are handled each as separate statements. So we are setting up 90, and then we're saying, okay, well, if the like now that I is initialized, then let's see if this is a truthful statement. Is 90 less than 0? No. Then we're not even going to go to the rest of it. We're not going to go to the decrement. We're just going to kick out of the loop. So we need to switch this to, so we only want this loop to fire while it's greater than or equal to 0. Man, I've been developing for like probably a decade now, a little bit over a decade now, and it's so funny when you get hung up on stupid little things like that. Okay, so now we have our step up to 90, which should, right, still not as open as I want it to be. Well, at least our open and closing is working. It's weird that we're setting it to 0, but we're still not getting the entire arc unless 0 is starting before. Unless the starting point really. 0 is probably past close. Okay. Well, looks like we're experimenting. So let's start this at. Let's say the starting angle we'll set to 40 and say 40 to 90. Let's see. So let's replace these out so we can more easily adjust them. Okay. So I think that the reason why we're seeing this odd opening and closing, and like it's weird because I didn't see this like on the previous pass through of this, is because the starting angle of the servo. So the servo rotates between 0 and 180 degrees, and if 0 is if 0 is past that close of the lid, then going to the 0 point, the 0 angle, would make it look like it's closed, but it's almost like it's pulling it more closed than it should be. So we can start feeling out what the actual open and close is by setting these variables and just giving it a try. I mean, I could probably pull it out and use the servo tester to say, okay, where's your starting angle, and then move the horns accordingly, and maybe I'll do that in the end. But ultimately, like right now, I'm trying to fit pieces in, so it doesn't matter. So okay, so we know that this ending is not high enough for what we want, and the opening. Let's see, how close are we getting? Okay, it's not closing completely. So let's change the starting angle to like 30, and let's change this to like 120. Let's see where we're at. Okay, how are we doing? Well, that's not bad. Okay, it's like, so one of the things that you have to be concerned about, or that I need to be concerned about here, is making sure that the joint for the servo and the linkage doesn't overextend. Okay, and it doesn't. So because basically, like, the lid's closed like this, and let's see, the lid's here. So what's the best way to explain this? So the linkage is kind of like this whenever it starts. And then as the servo pushes the linkage up, it's going to hit a point where The two are collinear, so both linkages are fully like basically it's fully extended, and that's fine. That's where we want that opening point to be. But if you keep going, you get this like overextension, like almost like if you overextend your knee. We don't want to hit that point. And you can go through and you could do the calculation with Grashoff's law to figure out like where's the non-binding point for the linkages, and I kind of did that when I was designing the linkages themselves, but it's over by just a little bit, so we just need to make sure that we don't overextend our angle. And it looks like this is fine. So opening, yeah, that's fine. I could probably make it end it a little bit sooner to make it safe. Let's see, what's the closing? And that closing looks fine. I mean, like, it's not going to close all the way because the cables are running through right now, but I think that this will be a good starting and ending point. And actually, I'm going to pull these up because I'm not completely sure. I'm not sure why, like, the starting and ending point that I had in the previous run are different. And I'm not sure why, if I'm, like, explicitly saying, okay, start at 0 at the very beginning, why we would get a difference. And actually, this should be starting angle. Okay. Okay, well, anyway. So, we want to fit, we've got, like, the servo fit into the code. The next thing I want to get into the code is... let's do the ultrasonic sensor next. Okay. Ultrasonic sensor. So, the way that this ultrasonic sensor works is there are two... I can't remember the term for the parts of the sensor. But basically... we generate an ultrasonic pulse that fires out of one of these, which is the trigger, and then it bounces off of something, and then we, on the echo, we listen for if that pulse came back, and if so, how long did it take to go out and come back. So we've got we got 4 pins. We got the voltage, the ground, the trigger, and the echo, and also something to point out. I don't know, I can't really zoom in easily here. But basically, I'm using the Trinket M0 uses 3.3 volt logic, but the ultrasonic sensor, the echo pin outputs a signal at 5 volts, which is what it takes to power the ultrasonic sensor itself. So if we send the 5 volt signal back into the microcontroller, we'd blow out our GPIO pins. So I've got 2 resistors in there in the circuit that I'm using as a voltage divider to step down the 5 volt signal to 3.3, so it's safe to go back into the GPIO pin. So the wiring's done, so let's actually set it up. And while I'm in here, let's start marking out areas. So okay, so I'll do the ultrasonic config so we know that we need do I want that? No. I'm just gonna leave them all up here. Okay. Oh, wait a minute. Nope. We need the trigger pin, and then we need the echo pin. The trigger pin on this is connected to 4, and the echo pin is connected to 3. Change my mind. This is so dumb. It doesn't really matter, but for the sense of cleanliness and readability, I'll group them all together. So for the ultrasonic sensor, we just need to do the regular Arduino pin mode. So pin mode of the trigger pin is output. pin mode of the echo pin is input. Okay, so we've got those set up, and then we need to take a reading. So this is a part that I'm probably going to have to look at the previous version of the code a bit, because I don't have it, I mean, like, conceptually what we want to do is we want to send out the ultrasonic pulse, then we want to read in the ultrasonic pulse from the echo pin. I am going to cheat. Now look at my previous version of the code. So what do we do? So we write... Okay, that's right. We write to the trigger. Oh. First we write a low signal to pull it down. And we delay it for like 2 microseconds. And then we write it high. So, and this is our pulse. So we're just saying, like, prep the trigger pin, set it low because we're about to send a signal. And then we're going to set it high for 10 microseconds, and then we're going to set it low again. We don't need the delay. So, so we just went, like, from low to high, we just went, shut it out if you want a sound effect. And now that we've sent out that pulse, we need to read in the duration that it took for that pulse to get out. So we do that with a float. Duration is pulse in. So pulse in will read in a pulse from the echo. We'll set that to high. So we're looking for when the pulse is high. And then the distance. The distance is, what is that? It is the duration times the speed of sound through air, which is 0.0343. Maybe the order code. Yeah, that's in general divided by 2. So the reason that we're doing so we've read in the pulse. We've read the pulse in when the pulse is high from the echo pin. But then to translate that duration, like how long it took for the ultrasonic pulse to go out, hit something and get back, to turn that into distance, we need to factor in the speed of sound. So we multiply the duration that it took by like the general speed of sound. Like this value changes based on like humidity and temperature, because we're talking about like a literal wave moving through air, particles in the air and bouncing back. So they're like since air is a fluid, that fluid's viscosity or consistency can change. So we're doing that to change it into distance, and then we do a divide by 2, which can seem kind of arbitrary, but when you think about it, we're shooting out a pulse, and then we're measuring it coming back, and then we're converting that to distance. But as far as like distance traveled, we went out and then came back. So if we want to figure out just the distance from where we are to the thing that we hit, we have to divide it by 2. It's almost like, it's like similar to a radius and diameter when you're talking about a circle. Right now we care about the radius, so we need to divide by 2. Forget the radius and diameter. We're dividing by 2 so that we get just the distance in one direction. So now we should be able to let's see. Distance to object, and then should be right. Boom, 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 boom. Yeah. Let's see what we get. Great. Oh, we've still got the serial print from. I'll just comment them out. So here's why we need a state machine, and it'll be even more obvious whenever we add the LED effects in, is because um, we're doing this like millisecond delay. We're doing our read, doing the millisecond delay, um, and but then we're going into blocking code. So to make the server, yeah, see, we see our distance right here, but we're not firing it again until the loop fires again. But we can't do the loop until the rest of that code fires, and we're delaying the microcontroller by 100 milliseconds twice. Or no, God, we're delaying the we're delaying it by 100 milliseconds per loop twice. So we get this giant pause between readings. So I'm going to comment out the code and move it out of the way. And this is why we need a state machine. So this is why we could potentially need a state machine depending on how we decide to actuate the lid. If we want to be able to continually take readings and then also move the lid up and down at the same time, and then fire the light pattern from the LEDs, we can't have delays in our code. We can't have blocking code that's going to stop the microcontroller from continuing to do the measurements and stuff. So, but I'm not going to even try to do the state machine here, partially because I want to think through how I want to apply it, how I want to apply it, but then also because we're just trying to fit stuff in now. But now we should see, let's see, let me do it here so you can see. As we get closer, our values drop, and as we move out, our values extend. So, and this is not perfect. I mean, it's using echolocation. It's like, you could think of it at like how a bat, determines how far things are away. Which means that if you have an object really close to it that's super thin, maybe it's going to hit it, maybe it's not. Or if you have an object that you're getting this really broad idea of distance, so it's not like you're able to really distinguish between fine detail of distance, but that's fine for what we want. We just want in general to know if someone's standing in front of it. Okay, so let's get that top of loop. Yeah, where do we have top of loop? Oh, we have top of loop at the bottom of the loop. Forgot about that. Alright, let's get that one more clean serial output, and then we'll start fitting in the LED strip, then talking a little bit more about the next steps. Okay, there we go. So that's a little bit easier to read. Again, not perfect. And this, I believe, is measured in centimeters. And we could put in a little bit of a delay. Realistically, what we're probably going to do with the state machine is build an interval for reading this, so that instead of getting just the raw output at the speed of the microcontroller, we can either do an interval so it reads every so many milliseconds or something like that, or we could potentially do sampling where we collect a bunch of information for a really short period of time and then average it, and then based on that do something. But either way, we're not trying to tackle it here. So, all right, we got the servo, we got the ultrasonic sensor. The last part is the LEDs. So the LED strip is already in there. It's already wired up, and I'm using the fast LED library. And actually, let me show. What am I gonna show? Do I have it up? I'll just show the previous version of the code. So this is the code that I wrote out earlier whenever the mic wasn't on. And I'm using the fast LED library, and I'm using their example of the Fire 2012, written by Mark Kurzman, which is really cool. It gives us really cool kind of dynamic simulation of fire that is adjustable with some parameters. Normally, I don't like to copy and paste. Even with my own codes, I just rewrote all of this from scratch, or I'll transpose so that I could better wrap my brain around what's happening. But in this particular case, the function here, would be really cool to go through a deep dive on and really understand how it's working. But right now, I'm gonna black box this and move it over. I feel like all my coworkers are gonna give me hell about this, but I don't really care that much. Okay, so we've pulled over our function and some of the settings here. Leave the comments in there so we can read through. Well, so I can read through them later. But then there are a couple of things that we need for the for this to work as far as definitions. We need the pin. I'm gonna close the monitor. Sometimes VS Code lags a little bit if you have the monitor just outputting. Whoa, won't even. Weird, I guess I'm not closing the serial monitor. So we need the LED pin, and that is on 2. And then we need the, hold on. What am I doing? Hold on. Let's split down. Okay, there we go. Okay. So we need the LED pin, we need the number of LEDs. This is going with the naming convention of the function. So our strip has 30. We need the color order, which is GRB. Chipset. Set the brightness to 200. Then set the frames per second at 30. Let's see, is that all we need? Oh no, yeah, that's right. We need to set whether or not to reverse the direction. Then we need to create the array of LEDs. Okay. So basically, we're going through and like defining some of the variables that function needs to fire. It's the pin, the GPIO pin that the LED strip is attached to, the number of LEDs on our LED strip, the order, the color order, like an instruction order that for the signals being sent to the LED strip, the chipset. I'm using NeoPixels, which use the WS2811 LEDs on them, so I can leave that the same. The level of brightness, and then the frame rate for the animation, whether or not to send the animation forward or back, and then our array of LEDs, so we can assign the individual indexes of the array to correspond to the color to set to the LEDs. So now in the setup, we need to, oh yeah, this I definitely don't have memorized yet. And send in that template with the chipset, pin, color order, the array, number of LEDs, and then we set the correction. I don't know what the correction is. I'm not gonna do a deep dive into this. So the color correction used for this controller. Yeah, there's more stuff that I need to read into as far as like understanding exactly what fast LEDs is doing here. But from their example, we start to get an idea. Oh, okay, it's a enum that's backed by a hex number for the color correction. So, yeah, not totally sure. It's following examples, so not worried about it. And then set the brightness of that. And so now in our loop, so you can think of the loop. If you're familiar with animation like CSS or game development like Unity or Unreal or like 3D development, or these are all the things that I've seen it in, like 3D development with things like 3JS. There's this concept of frames, or like film. Like there's this concept of frames, and basically at the beginning, like as you're looping through, you're setting up what should be drawn out to like the screen in the case of animation, or the LED strip in the case the case of this LED animation. So you're writing all that out, and then you're essentially sending it down to the strip or sending it to the screen. And then the motion, that the animation is really just a combination of the setup of all of those frames tied to the passage of time, which is a really weird way of saying it. So, but like if you, well, I'm not gonna dive super deep into it. Animation is very cool, especially whenever you can unhook the animation from time and have it step forward or step backwards and stuff like that. But what we need to do to make this fire animation fire is to call the function that does the setup for what the strip should be, what the values of the LEDs in the strip should be at, for this particular frame. So fire, call that. So that will arrange the LEDs, the LED colors, and then fast LED show. This will write all that information down to the strip, and then delay. And then this, from the example, is just setting up that frame rate. I have to do a deep dive on the fast LED delay to understand why it is separate from the just the regular Arduino delay. I kind of suspect that it's so that you could do things like a state machine, so you're not doing a complete blocking of the code. Like this is probably backed by a state machine, but I don't know yet. I haven't dove that far into it. So, but this will go through, do our animation. Let's upload it. Look, rather than listen to the top. Huh, that's weird. Are we getting color? So, I must have missed something. GRB. That's oh, forgot to import the library. That also explains, like, I wasn't seeing some of the type hints I was expecting to see. Message. Okay, cool. Yeah, if you want to compile your code, it helps if you actually put it in there. Oh, and the lid's closed, so we can't see it. We've got what we need from here at the moment, so let's see. Let's put it up at, open the box right at the beginning so that it just opens up and stays open, and then we can take a look at our animation. Cool. Alright, so now we've got our LED strip, and actually I'm using hopefully the lag on my cell phone camera isn't so bad that we can't see this well. but we've got this really cool LED animation simulation of fire. And then and this function is really cool. Like it goes through and and basically it sets a temperature for each of the LEDs, and then adjusts that so that it's the temperature is is tied to the color, where the more red is the low value, I believe, and then the white is the high value. And it's between 0 and 255, and then each animation frame, you see the the LEDs cool down, but then there are also sparks that add in this random heat and stuff like that. And there's I don't know, there's a bunch of settings in here that can be adjusted, and it's a very cool simulation. And also to show the idea of frames and of stopping with time. Let's just show. I wonder how this is gonna look. Oh, wait a minute. If we do it in the loop, it's still gonna update. Oh yeah, without the frame rate, it's just gonna go super fast. For a moment, let's move it up to the setup so that it only fires once. So it's going to do the prep for the information for the. Oh, okay, here we go. So the this is. Oh shoot! What we saw was one frame. Oh, wait a minute. So we're seeing one frame here, which is just one lit up LED, which isn't really showing what I wanted to show. Let's just blow out the frame rate, and let's do blocking code and make it 5-second delays between each of the animations. Okay, so this is the frame rate. It slowed down to every 5 seconds. So each time the loop fires, and of course I remove the top of the loop, but we can kind of see this because we know that this distance sensing or our distance calculation is only firing once per loop. So we're doing a really heavy block, a 5-second block of each loop that is happening. So for each of those frames, we're getting more and more of the fire. So actually it's really cool seeing this slow down, because I think that the way that you can look at this, or probably should look at this, is up, where the root of the fire is at the very bottom, the hottest parts, and then as we move up, we get kind of the idea of the heat being dissipated through the air, so things aren't nearly as hot as we move up. And what eventually what you'll see, when we're starting to see it now, is little sparks of heat there that are being introduced and then rising up and stuff. So each 5 seconds, we're seeing this frame where the function is firing and prepping the entire state of the LED strip, and then writing out to it, and then stopping. So if we tied this to a button, we could manually advance time and see each of the individual frames. And if we are tracking the state, the state changes of this array, we could potentially move backwards and forwards through time. So, and I think it's just really cool to show this kind of how animation works like this, because this same concept works for things like drawing animation onto a screen, in WebGL, or doing a CSS animation. You're setting up individual frames and then advancing it with time. I don't know. I think that's cool. But okay, so this is all of the pieces fit together, and now the last thing I'm going to show in this video is why we need a state machine. And we saw this a little bit already, but if I enable the loop, and actually we see it right now with the arbitrary 5-second delay, if like we have these three core concepts within the code that we want to encapsulate, which is the servo moving up and down, the LED strip animating, and then the ultrasonic sensor distancing, or detecting the distance. And if we write blocking code, we're going to experience what we're seeing now, which is each of those pieces happens one at a time. So we detect the distance. Now we animate a frame, then you fire the ultrasonic sensor to detect the distance, and then we go through this loop to actuate the servo, to actuate the lid up and down, and then we start over again, and we can't build an experience out of this, at least not a very clean one. So now that we know that all of our pieces are working and like the code, like the basics of the code are in place, now we can start to introduce a state machine, which will be able to create an interval on which things should happen, like different things should happen, so that whenever like we can let our loop run, we can not write any blocking code. And then like if the interval, like for a given loop instance, if the interval for a particular thing is ready, then we can fire it, but if not, we could just skip it and check to see if any of the other intervals are there, or are up, which is probably not a clear way of explaining it, but I don't know, when I do the second video, it will make more sense. So, but what we'll probably end up doing is, the main thing that we want to trigger all of this is the distance away from the lid. So we'll probably we'll have an interval for the ultrasonic sensor, either an interval or sampling, where we take a bunch of distances and then we only fire the rest of the animations based on like the average of that sample. But basically, we'll have some kind of a way of checking the distances, and then a threshold to say, okay, once you get closer than this distance, now I want to start opening and closing the lid, and then a translation of that to the angle that the lid should be open. So it'll probably be for the ultrasonic interval, we'll check it every so often. And then if the current reading is closer than a certain threshold, then we'll say that we should start doing the lid actuation interval, and then it will be able to open and close, and like while the distance sensing interval is still running, and we'll send live updates of what angle it should be, and then the light animation, once we're past that threshold, should just run. Like it's just like fire the light animation function, and then fit that in with the other intervals. That's probably how we'll do it. I don't know. We'll see when we get to that point. But that is kind of where I wanted to be with everything. So I'm gonna go eat lunch.